Wait, where did they put
It's because he gave those are the changes that we did.
Where do we turn it in?
Right there, like where we were standing, should be a pile. Okay. All right, Ryan, Show, you got the camera working over here? Because there's big news. All right, yesterday was the big reveal, right? But oftentimes, it's only the next day when you get to really absorb the deep impact of what just happened. All right, so you've had 48 hours to let these ideas marinate and to do your homework and reflect upon what it is that we learned. And now you are ready for what we are now going to do is engage in a reinterpretation of this entire unit. Because after all, we did a whole bunch of crap with matrices, right? All the while without understanding what the hell a matrix really was. And now, knowing what a matrix is, all concepts have to be reevaluated. Okay, what am I talking about? Well, first, an activity. A simple activity, and if you get a sudden flash of insight, just keep it to yourself for a minute so everyone can have a chance. Alright, please do the following. I will give you a vector, I don't know, 5, 2. And here's what we're going to do with that vector. First, with this vector, reflect across the x-axis. Then, rotate 90 degrees counterclockwise. I'll write that again. So, reflect across the x-axis, then rotate 90 degrees counterclockwise. The vector 5, 2. Everyone just do that. Take the vector 5, 2, draw the vector, reflect it across the x-axis, draw that, and then rotate that by 90 degrees counterclockwise.
Yeah, let's get 2-5. 2-5.
And all of you people at home, you need to do this too. Take out a piece of paper and take notes and all that kind of stuff.
It says counterclockwise. So you have to use your eyes.
But you don't
And then he changes it.
Alright, everyone relax. This is not that hard of a problem. Take the vector 5, 2, reflect it across the x-axis. I get 5 negative to agree. Okay, now I want to rotate 90 degrees counterclockwise. Where do I end up?
2-5.
Up here at 2, 5. That was a relatively simple task. I'll call that a double prime for the image of the image. Okay, cool, great, wonderful, no big deal. Now, please instead take the vector 5, 2. First, rotate 90 degrees counterclockwise, and then reflect across the x-axis. Yeah, so if you rotate 5, 2, 90 degrees clockwise, you get negative 2, 5. If you then reflect that across the x-axis, you are going to get this vector, a double prime, which is -2, -5. Everyone good? All right. What, Alice, what is the significance of this? Different. She says not interchangeable. Okay, yeah, so step one. It is simply a fact of geometry that it matters which of these you do first, right? This, if I first reflect across the x-axis and then rotate 90 degrees, I'm just going to get something different than if I first rotate and then reflect. Has everyone fully absorbed that? Okay, good. All right. What does it have to do with matrices? Well, maybe some of you are seeing it already. If you do, just like a gasp in wonder. I could maybe think about doing this with matrices, because that's what we've been doing after all. What is the matrix which reflects across the x-axis, by the way? What matrix? This should take now about 5 seconds to produce this matrix. Reflecting goes x 1, 0.
0, 1.
Stays the same, right? Yeah? So it's still 1, 0. And 0, 1 goes to? Wait, -1, 0, right?
Yeah.
Is that what we said? No.
0, -1.
0, -1. Whoa.
How you pull it.
That was wrong. My dude was right. Okay, and then what is the matrix which rotates 90 degrees counterclockwise? Okay, we'll mess up this time. 1, 0 goes to?
0.
Goes to 0, 1. And 0, 1 goes to?
-1.
-1, 0. Okay, good. Alright, so, suppose you had a particular vector and you wanted to perform this sequence of geometric transformations on that vector. Well, if I first want to reflect across the x-axis, then the first thing I'm going to do is to plug that vector into this function. Agreed? Did I agree? Okay, good. So I'm going to take this matrix, the reflect across the x-axis matrix, and I will feed it my particular vector, xy, that I wish to transform. Now, this being a 2 by 2 matrix and this being a 2 by 1 vector, when this eats this, what comes out? A vector, right? And that vector is the result of reflecting across the x-axis. So when you see this product, do you see that it is simply just a vector? It just is a vector when you multiply it out. Okay, well what am I going to do with that vector? Now, I'm going to take that vector, and the next thing I need to do is rotate it 90 degrees counterclockwise. And so I'm going to plug this vector, so to speak, because it really is a vector, into the rotate me 90 degrees counterclockwise matrix. Whoa.
It's like function
Cool.
composition.
Yeah. All right, conversely, if I first want to rotate 90 degrees counterclockwise and then want to reflect across the x-axis, then I would start with my vector, and I would first plug it into the first I need to plug it into the 90 degrees counterclockwise matrix, right? Because that's the first thing that happens. So I first plug it into this matrix, when I do that, I get a vector. There's a lot of suspense going on now. And then what do I do with that vector? After I rotate 90 degrees, then I plug it into that matrix, right? Yeah, then I'm going to plug it into the reflect across the x-axis matrix. Okay, so, and if I do this all out, I'm going to get, so what's going on here? Tell me what's going on.
It's matrix multiplication, it's not commutative.
It's matrix multiplication. This is just matrix multiplication, right? If I wanted a single matrix, which captures reflecting across the x-axis and then rotating 90 degrees, what could I do? If I wanted that encapsulated in one matrix, it's just like move the parentheses. Reynolds says, dude, matrix multiplication is associative, so he's like, move the parentheses, and then what I do, if I multiply this, if I multiply these two matrices, let's see, let me just do it. I think I get 0, 1, 1, 0. Yeah, which actually matches up with what I think is is going to happen. Yep. So this matrix, the product of these two matrices, is the result of first performing this operation and then performing this operation on an arbitrary vector. Whereas over here, if I multiply these two matrices together in the way that I've written them, again we can just move the parentheses, then I get 0, let's see, -1, -1,
0.
0. And that is the result of first rotating 9 degrees and then reflecting across the x-axis. So what is matrix multiplication really? Everybody, who knows? Which is I think at least half of you. Yeah, what is it?
Transformations.
It's like two transformations back to back. If a matrix is really a function, then what is matrix multiplication?
Function multiplication.
Yeah, there's a name for that. Oh wait, this isn't working the way it usually works. Are you guys just being shy?
Perhaps.
Ryan Cho, what is matrix multiplication?
Function composition.
It's function composition.
I'm so smart.
Matrix multiplication, maybe I was just getting there because you didn't use the word composition. Yeah, when you do a function and then you take the result and you plug it into another function, that's called function composition. So matrix multiplication is just function composition. Just like back last year or whatever, even in middle school, when you would write like f of g of x, you would even write it like that, right?
Wait.
F of what? F of like that, right?
Yes.
Yeah. Better. F of g of x. But really, what's I guess what's important is that, and some people would write it the kind of fancy way where they'd go like f compose g,
Fog.
you know, of x, right?
Fog.
What is the f compose g function? The f compose g function is a function which, given an arbitrary input, first plugs it into g, and then the result comes out and plugs it into f, which is maybe counterintuitive to you when you're like 11 or whatever. It's the same thing here, right? xy is the input. This vector first goes into this matrix and then into this one. Function matrix multiplication is just function composition. It's amazing. When you take a linear algebra class, they will derive the rules for matrix multiplication in such a way that by definition it is supposed to do function composition. And Sally even said something more awesome. I don't know if you guys were ready for it yet. Sally, say it again.
It's not commutative?
This solves the giant mystery, which previously was just a blank space in our brain. Why, really, on a deep level, is matrix multiplication not commutative? Reason.
Because you're doing two geometric transformations.
Because you're doing two geometric transformations. And Justin says the fundamental geometric transformations which the matrices encode are themselves not commutative. So of course matrix multiplication can't be commutative because function composition is in general not commutative. And we've just seen that. Get it? Are you feeling enlightened? I'm feeling enlightened. I already knew this. Hooray. Good. That solves the entire mystery of why matrix multiplication is not commutative. Oh, but there's more. Again, as I promised, we are going to reinterpret all of the things we did all unit in terms of this new understanding of what a matrix really is. Catherine, what's an inverse matrix?
The number that when multiplied by a matrix you get the identity.
Yes, that is the absolutely correct yet dry and boring original definition that we said. A matrix, an inverse of a matrix is just the matrix which when multiplied with the original gives you the identity matrix. Would someone like to give me a new, deep, geometric, compelling, mind-blowing understanding of what a matrix actually really is? Inverse. Oh, Isabella, sick. Ryan Cho, you're up. What is an inverse matrix really?
Inverse matrix is when multiplied.
Nick.
Isn't it the thing that, like, the function that would return x if plugged into the...
Yeah, if a matrix is a geometric transformation,
Okay.
then what should an inverse matrix do?
The inverse matrix should bring you back to the unit.
Yeah, it brings you back. The inverse matrix is just the geometric transformation which undoes what the original matrix just did. Okay, examples. Take the matrix 3, 0, 0, 3. What does this matrix do? It dilates. So what is the inverse of this matrix? Well, we can just, everyone just compute it really quick. What do you get? Yeah, 1 over the determinant, which is 9, right? Yeah, times the matrix that you get from switching those two and multiplying those two by -1. So it's just this. Whoa. Dude. This is like it's like you have you have your unit vectors and you have your unit square, and the original matrix dilates by a factor of 3 to produce the 3 by 3 square. And then what does the inverse of that matrix do?
Brings it back to
It just dilates it back. It dilates everything back to the unit square. Whoa. Would you like to see another example of this?
Yeah.
I think you would. Here's another example. Take this matrix, 1, 0, -3, 1. First of all, make a picture and figure out what this matrix does by drawing the unit square and the transformations. No. I don't know what you're talking about. And then construct the inverse of this matrix. This matrix sends 1, 0 to 1, -3, and it sends 0, 1 to 0, 1. So is this what you guys got? Alright, so what is this matrix fundamentally doing? What geometric transformation is it doing?
Shear.
It's like a shear, yeah, it's a downward shear by scale of 3. Okay, so call this matrix like A or something. What does the inverse do? Let's calculate the inverse. What do you get? 1 over, what's the determinant? 1 times the matrix which those two get switched, and then these two get negatives. Cool? So, okay, well what does this matrix do? It just shears back up, right? I mean, I can also make a picture of this matrix. Here we go, unit square. And then it sends 1, 0 to 1, 3, and 0, 1 to 0, 1. Yeah, so if the original matrix shears down, the inverse matrix is a terrible picture, shears back up. Cool? Okay, good. What else is left? And now I feel like I'm doubling my intelligence and understanding of everything. An inverse matrix is really just like an inverse function, right? It undoes what the other thing does. What else is left? What's the other thing you're supposed to be asking me about constantly all units? What is a determinant? So what, does anyone have an idea? What does a determinant, there's actually a lot of possible answers. What does a determinant tell you? What were our old definitions of determinant? Landmarks, let's do them all. Old definitions of determinant. No, you give me the formula. I don't want the formula. I want the understanding, Lily.
Oh, I have something for you.
What? You want to talk about the new thing?
Yeah.
Okay, I'll do the old ones then. You give me the new. The old ones are, it was the thing which tells me whether the matrix is invertible, and it was the area of the parallelogram determined by the column vectors, and probably some other stuff too. There's a thing that tells you about linear independence, and was there anything else thing that shows up in the denominator? Okay, Lily, how should I think about a determinant now? If the matrix is really a geometric transformation, what does the determinant tell me?
It tells you like how much it's been like transformed.
How much it's been transformed. Randall, were you gonna say something like that?
No.
Justin?
It seems to have a big play in like scale.
It seems to have a big play in scale.
Yes, to
These
scale your back,
two
scale it
are
down.
onto something. Lily says it tells you how much it's transformed. That's a little bit vague though. Justin says it has something to do with scale.
The scalar value.
We just did two determinants. Look at, what were the two that we just did? This one we just did. This was a determinant. And this was also a determinant.
Oh, it's the area, how much area is multiplied by.
Yeah. It is, they were both right, but Reynolds said it exactly. It is the determinant of a matrix is the factor by which the area of the figure increases.
Oh my gosh.
That's right.
Oh my god.
What are some examples? Take this matrix, or take this determinant, 3003. This is the one we already saw, right? What is the determinant of this matrix? 9. And as we see, 9 is the factor by which the area of the unit square increased. Yeah? And in fact, not just the unit square, but any figure will be increased by factor 9. And then the other one that we just did a minute ago was, what's the determinant of 1, 0, negative 3, 1? What was that determinant? 1. What is the interpretation of this? Yeah, it's the factor by which the area changed in this case, but as we discussed last class, this is a shear, and shears are area preserving. Cool? Okay, and then finally, I'll give you another one. All right, here's some crap. 2, 3, 4, 9. Okay, I'm going to tell you right now that I have no idea what this matrix does. I would struggle a lot to try to put it into words what geometric transformation this is. Fact of linear algebra: all matrix transformations are just compositions of reflections, rotations, and dilations. So every single thing you can do with a matrix either reflects, rotates, dilates, or some combination of all three of those. I have no idea what this matrix does, but I can tell you one thing. First of all, what's the determinant? 6. So what I can tell you is that this matrix will increase the area of any figure by a factor of 6. So, for example, let's do one or two more quick problems up here. For example, take this matrix, this 2, 3, 4, 9. I want to kind of do this fast, so instead of giving you guys 10 minutes to do it, let's just do it really fast. Take this matrix. I have no idea what this matrix does. And let's feed it a triangle. Let's feed it the triangle 3, 1, 8, 1, 3, 3. Okay, do that matrix multiplication really quick, or like one person per table do it and everyone else copy. And now I'm going to make a picture.
You're doing it.
I always.
Okay, I graphed it. I get a little tiny right triangle. Agree? What is the area of this little tiny right triangle?
1/2 base length.
1/2 base times how you got this.
5
I think
times
it's 5
It's 5.
times
5.
2
5.
divided by 2.
5.
Yeah, so the area of this triangle is 5. I agree. Now, what happens when I perform this obscure transformation on this triangle, I get new numbers. Did anyone do it? What do we get? Give me the vectors. Actually, I just did it myself. I got 921, 1941, and 1539. Agreed?
Indeed.
Okay, so what I'm going to get is some kind of disgusting triangle that I don't even want to talk about. It's so disgusting. That's not really right. 921, 1941 is like going off my paper. 1539 is like over here or something. All right, so I don't even want to talk about this triangle. It's so just ugly and weird. But there's one thing I can say about this triangle for sure.
It's 30.
The area is 30. Because the area of the original triangle was 5, and this triangle increased by a factor 6 because the determinant of the transformation is 6. Cool? Okay, last thing, and then this unit is basically over. We need to talk about the killer. And as we talked about, there's not just one killer. This is also a killer.
It makes the
This is a kind of killer matrix. What does this matrix do? Well, what does it do? It's actually unclear what it does. What? What's the determinant of this matrix?
0.
0.
Oh, so it makes it 0.
There's so many things to say right now, but it's lame if I have to say them. Let's perform a translation of something. So 5 2 1 2 5 4 1 4. Okay, do this matrix multiplication, or do it on a calculator, or copy up the person next to you, whichever one's faster.
wait, what? I'm not a calculator.
You're a guess.
Never trust us.
You're smart.
So smart.
I'm right, kid.
Actually, it doesn't take that long.
Wait, I'll go second. Take myself. You're good.
What? 2 plus 12 is 14.
I got that. Actually, it only takes like 30 seconds if you just know what you're doing. All right, and now I'm going to graph all this stuff.
Wait, I gotta go on to a new page.
And 1 4. Okay, so here's what I got. I got 5 2 1 2. Call this point A. Call this point B. I know the picture's kind of tiny. Then I have point C, which is 5 4. And then I have 1 4, which I'm calling point D. This is, I believe, a rectangle. Do you agree?
Yeah.
What is the area of this rectangle? I believe it is 8. Yeah, it's a 4 by 2 rectangle. Okay, wonderful. Now, let us transform this rectangle. Are you ready? Some excitement building here. Okay, so 5 2 gets sent to 27 18. So let me get some kind of scale going here. 10, 20, 30, 40, something like that. Okay, so 27. 27 18 is like over here. That's the point 27 18. I'm going to call that A prime. Cool? Okay. Now I have the point 15 10. I'm going to call that B prime. 15 10. Everyone following this? Just doing it. Then I have a point 3926. C prime 3926. And now something very curious happens. What happens when I transform the point D, which is 1, 4? It also goes to A prime. What the hell? Okay, someone talk to me. So many deep things are happening. It's like actual math. Mark, tell me one observation. What is this matrix doing? Putting them in a straight line. Yeah, I believe this is the line like y equals 2/3 or y equals 3/2 or some crap like that, right?
3/2.
Yeah. Yeah. So this is again a killer. If you didn't believe me before, do you believe me now? This is killing. Okay. More deep comments. Yeah, Sally.
The slope of the line is 3/2 or 6/4.
Yeah. I think it's actually 2/3.
No,
the
3/2.
slope, right? The slope is 3/2? No, the slope
Oh
is
no, I'm
2/3.
dumb. I'm dumb.
Yeah, I think the slope is 2/3. But yeah, okay, good. That's an observation. What else? Talk to me about what this all means. What do we know about this? Yeah, Alice. Yeah, the area kind of went away. Okay, that's consistent with our understanding of the determinant, right? As giving the scale factor by which the area changes. What's the area of this new figure? It's just dead, 0, right? So that's good. But there's more deep things to say. Yes?
The original killer one that was just 1, 1, 1 was basically the same thing because it gives you a line with slope 1.
Yeah, she's talking about the other killer, which is still up there on the board, right? That also has determinant of 0, right? So when so I now understand that when the determinant of a matrix is 0, it's telling me that the area is collapsing. But there's something even deeper to say. What was our Reynold?
I was thinking like, can't be undone.
Can't be undone. Whoa, elaborate.
It's like the inverse takes the determinant, put it under 1, and then you can't do 1/0.
Yeah, Reynolds trying to really make it happen. This whole unit was about matrices, and our original understanding of the determinant is that the determinant tells you if the matrix is invertible. Okay? So what does it mean if a matrix is not invertible? What is it saying about the matrix transformation itself if it is undoable? Alice? I kind of said it, but there's more to be said. What does it mean for a transformation to be undoable? It can't be reversed. What kinds of things could you do that can't be reversed? Yeah.
You can turn like a box into a line, but you can't turn a line into a box.
You can turn a box into a line, but you can't turn a line into a box, she says. Yeah, that's pretty deep. It's kind of a poem. Yeah, you can have a giant triangle and you can collapse it. Why can't you turn a line into a box?
There's too many points.
Because there are too many points on a line to get the box back or something, right? Can you say, I made this example to specifically address this issue. No one seems to be pointing to the issue at heart here. What is it about this matrix transformation? There's like math vocab that could be used here. Yeah, Lily.
There are no vertices?
No, the heart, I feel like the heart of it is this point. What happened here? This is